I'm not very presentable. I'm facing a lot of fever, cough, and all that. So I'm not showing my cam because I don't want you guys to be, disguised with my running nose or something. Okay, so in today's session, we are going to build a ray tracer. And I'm going to dive into first that what is a ray tracer at the first place, and how it works, what is the state of the art, and where does it begin, and all those. Okay, so yeah, we are doing this session for AICTE, and we have with us a lot of teachers right now. So all the faculties are with us, and we are sort of having these sessions for them. First, if you guys, I would love to know, I would love to have a conversation about last sessions. What was the last session about, and how far you are to understand rendering and all those stuff? Would love to know. Yeah, can you guys hear me? Yeah, sure. Surely. Yeah. I think I lost audio. 1 second. Uh, Hold on. Yeah, now you are audible. Yeah.
And I think we need more practice for understanding these techniques, because I understand they are very tech.
Okay, they are very tech heavy. Okay, surely understand. And I'm definitely losing a lot of audio, a lot of connection issues are there. But let's see how far we can go and how far we can keep up. Okay, so let me just quickly show you how far ray tracing is right now. Okay, so we are going to talk about this particular technique of rendering, and okay, so you got the idea, right? So what is different in this video than other games you might saw on the internet or anywhere else? So talking about these is ray trace renderer, and ray traced is one of the two major rendering methods. Okay, in the previous sessions, which was related to computational thinking, I told you what is rendering, right, and the step of rendering. I would love to show that slide once again for convenience. Okay, or you might have forgotten that in some sessions which happened in between. So let me share that slide. Yeah, which one? This one. Yeah. So in this computational thinking slide, you might remember this section, this specific section where we talk about this process, right? Okay, so this process is specifically belong to one method of rendering, and which method it represent? This is rasterization. Okay, you might already heard the name here. You can already say it's oh, hold on, let me present, then the screen will be bigger. Okay, you might already see here is a rasterizer. Okay, rasterizer and Raytracer, they are two most popular techniques. There are definitely other techniques as well for rendering the graphics. First of all, what is rendering? Rendering is the art of generating, or the science of generating, images from the code and algorithms. Okay, so whatever it's oversimplified definition surely, but it fits the scenario perfectly. So you have some sort of algorithms, and through those algorithms you have to generate some sort of images. Okay, so if you find Unity overwhelming, Unity is a physics engine, specifically a rasterizer. Okay, Unity does also support ray tracing in some form, but we have to do a lot of stuff for that. I'm not focusing on Unity's ray tracing, however it's going to be similar, but I'm going to focus on ray tracing from a very scratch, which means ray tracing from a C++ code. You know C++, you write bunch of lines, print hello world or something, printf hello world, and it prints hello world. So from that mechanism, from that bare bone structure, we are going to build an image generator. Okay, so that image generator is a rasterizer a ray tracer for now, and that we are also going to do the rasterizer in the second session. So my talk are related heavily on code, and it's the fundamental code. It's not, you can say it's not a tool based code, which means you have to learn a lot of tool, but for my session you have to learn a lot of basic science behind this objects. Okay, so I'm more of a code and science oriented guy. So yeah, it's going to be very tough because the prerequisites are very heavy. You need to know a lot of math, a lot of physics, and all those stuff. So for example, in math, you must have to know linear algebra, coordinate system, Cartesian coordinate specifically, and a lot of calculus is also involved in this, but we are going to take one by one, or most specifically linear algebra for now. Okay, so yeah, this is a rasterizer, but I'm going to dig into what is a ray tracer. And the way how rasterizer work and the way how Raytracer work are completely different. Okay, so let me first talk about what is a rasterizer. Okay, so I'm going to talk about rasterizer. I have already shown you, if you have bunch of vertices, you have to basically point the vertices as a vertex processor calculates a vertex or place it in the space in between, and then rasterizer basically test that is this vertex going to be colored or not, is this vertex belongs to the object or not. Something similar we are going to test in this one, but we'll see. And then finally the fragment rendering happens, and which basically decides that which color belongs to this particular vertex, this particular pixel. Okay, so that's the whole idea, and that's the whole process of rendering images in rasterization method. Okay, but let me talk about ray tracing. Ray tracing is a more natural method of rendering objects. You'll ask why? Because it's the most physically accurate method of rendering objects. If I talk about how light, oh, not this. if I talk show you some image, because I got no time to create this presentation, I'm going to show on a search image and show you. Okay, so I'm going to search about lights. Okay, that how light works. So if you this is not the light I'm looking for. How photon works. All right, or I must say how illumination works. I'm not getting a very good picture. What I have in my mind, I'm not getting it. Okay, this is good. This one is good. All right. Okay, awesome. So let me get a better picture, because suppose if I send, watch a picture here, or maybe this one. All right. Okay, so here is our sun. All right. You can see how the light works exactly. Okay. So if there is a sun, okay, the sun's light from the sun is going to be, going to fall on the surface. Okay. Why you think this tree is looking a little greenish? Because the light is scattering from the grass and then bouncing off on this surface and making it look green. Okay, this tree is not actually green, but it's looking green. All right, you will see similar example there. Okay, so this is called ambient occlusion. So oh sorry, ambient bounce. Okay, so suppose whatever the suppose if I see some more pictures. Photo. I'm working on today's session for 6 p.m. 6 a.m. Since morning, but still not got enough time to complete this slide, because the code which this involves is intense, and it's definitely not possible to cover in one day. It's a huge topic, and nobody has covered in one day or one session. So yeah, but still I'm trying my best. Okay, for example, this cave is the best example. Okay, why this cave is the best example? Because it's mostly black. The only source of light in this cave is some opening on top, and from that one ray of light is coming inside, and that is illuminating everything. Okay, so specifically in a scene in which very less light is there. Okay, so light comes from one direction, it bounces at a 90-degree angle to other object, it bounces again, the photon bounces again here, and to whatever the object the light is bouncing. Okay, light takes some color of that object. For example, if light bounces from a red object, let me also talk about the color itself. Okay, in physics. So suppose when we see a red object, we say it's red color. Okay, when we see, for example, this red leaf, we say it's red color. And it's if you talk to a physicist, he'll tell you that it's very wrong. This leaf is red because it has no red color in it. Okay, this leaf is red because it's observing all the other colors. Like the light is basically white, the white light is falling on this leaf, and from all the other colors are being dropped on this leaf. Okay, and only all the other colors are being observed by this leaf, but not the red color. So it's not accepting the red color, so the red color is bounced back, and rest of all the light is being observed. All right, so again, repeat after me. So the white light is falling on this leaf. Okay, all the other colors are observed, but not the red one, so it's not accepting the red color. So the red color is bouncing off from this. So whenever the reflection is happening, suppose the ray of light is coming from this direction, where my mouse is, and falling on this leaf. So all the other colors like blue, green, all the white spectrum colors are going to be observed in this. Okay, they are going to absorb, and the red color is not able to absorb in this pigment. Okay, so the red will bounce, and because the red is bouncing, now the bounced light from this is red in color. Okay, so this is the fundamental of how photon works, or how light works. Okay, so whenever the light is dropped on some object, it takes the color of that object, or whatever the color is not accepting, whatever the color is reflecting, and the light becomes that color. So whatever the light is coming from this leaf is now red, or whatever the bounce is coming from this leaf is now red. Okay, and then when the bounce will come from this leaf, it will fall on some object. For example, this particular leaf leg, whatever you call it, I don't know. Okay, I'm not a botany expert, so
Branch.
branch, yeah, branch is a good option. Okay, so when the red will fall off, or bounce off from this, it will fall on this. And how it will look like now, it had now whatever the ray of light is coming from this leaf has only red color, not any other color. It's not a white light which is coming from this leaf, it's a red light. So the outcome will be red. Here on this leaf it will be red, a little bit of redness will be add on. And colors are additive. For example, if I have to mathematically explain a color, I'll definitely say they are additive, which means if you shine a red light and shine a yellow light on some object, it will going to be illuminate red plus white, red plus a yellow in the same intensities. All right, so that's why the colors are always mathematically can be presented, and always mathematically additive. Okay, so yeah, talking about that, now we have a basic understanding of how light works in real world scenarios. For example, how shininess works. So the light is bouncing on the tiger, and from the tiger it's bouncing to the water. Now the water takes color of tiger, because from the tiger the color which is bouncing off, the light which is bouncing off is now yellow. It's not white light, it's a yellow light which is going to the water, and now the water is yellow. Same is happening on this as well. You can see this is why the bounces always have a color, and the bounce is never the white light, and the colors are additive, which means if this has no color, and this color will be added. Okay, so in mathematics it could be represented the same way. Okay, so now the problem with our rendering method is this. Let me explain. Ray tracing, not ray tracing uses. I'm trying to find something like this, but not actually like this. For some reason I'm not getting any good image, and I have what I want to show you in mind, but I'm not a very good artist, so I can draw that image. Okay, so no issues. I'm still trying to, yeah, this is very good. Okay, so this gives you an idea. In real world what happens is, suppose this image is masterpiece, I would say. Okay, so let me just open it. Okay, so you can see this image, and what is happening here. Suppose the sunlight, as I already told you the property of our light bounciness and all. Okay, so this sunlight is yellow, but sun is actually not yellow, sun is white. So the sunlight is it white, and sunlight go to atmosphere and changes some color based on whatever the width of atmosphere it's falling. For example, if the sun is in the sunset or the sun rise, the sun is sun is getting a horizontal cut through the atmosphere, and it's facing a lot of atmosphere. This is why the sun is either reddish color. The spectrum is stretched, you can say the wavelength is stretched, and when the sun is on top, the sun is yellowish. Okay, so the light reflects that way. You guys already know about that. Okay, so now the white light is coming to this red object. However, we could have represented a very good way on that as well. Okay, now for example, the sunlight is coming to that red object. Now the bouncing light from this red object is going to be a little red. Okay, you know why? Because this is how red object looks red, because now the upcoming light from that object is red light, not white, right? Okay, so the sun's light is becoming red here. Now this red light is there, and now on the blue cube there's going to be a little bit of red reflection, but there's going to be equal white reflection as well, because there's not only one. If I could draw on screen, is there a tool through which I can draw on screen? Let me just find draw on screen.
You can use Jamboard.
Yeah, I'm really looking for some tool through which I can draw on screen.
Simply keep this file in the bitmap. Paintbrush may open so you can draw on it.
Yeah, this is some software which basically may help me draw. Because this image is very good, but this image is a little wrong. So I want to tell you that how actually light works. If I had to tell you, I must show you in some ways, and I'm really sorry. I'm trying really hard from since morning, but I was not able to uh, make on time.
It's perfectly okay, Avi. Don't say sorry so many times.
Okay.
You're making an effort. It's perfectly fine.
Okay, so now the problem with this image is it's assuming and it's creating a wrong. Oh, what is happening? How do I go back? How do I go back? How do I go back to mouse? Okay, now it's back to mouse. Okay, awesome. Okay, so now the problem with this image is it's creating a wrong image that in mind that there's going to be just one ray. Okay, from the sun there are going to be a billion of rays. Okay, oh, it's too, width is too much. How do I reduce width? Oh, yeah. For example, इतनी मोटी रे समझ लेते हैं. Okay, so there are going to be hundreds of rays falling on all the objects, right? Something like this. Okay, erase. How do I select a width?
Below eraser.
Below
The black.
eraser.
Yeah.
Yeah. Okay, awesome. Okay, so there are going to be thousands of rays in all the direction and falling on all the objects on all with all the angles respectively. Okay, it's going to be something like this. Okay, now let me tell you what will happen. So for example, now the ray is which is going to be bounced from here. Okay, from this object. Now from this object all the white light is observed. Now only light which could come from this object is red. Okay, this is why this object is red to our eyes. Okay. Now what will happen if I select a color here? I think color is selected here, right? Now the object light which is coming from here is red, and the red light will fall on this object here somewhere. Okay, how will determine the angle? The angle is basically this angle this incident to this particular the throw off, and this angle has to be a 90-degree angle. Okay, so it's always a 90-degree angle through with wherever the light falls, it will bounce off to 90 degree. Okay. So similarly, from here the light is falling, but now here all sort of light is coming, so it's obviously blue. It's obviously because if I tell you this is going to be red, then I would not able to tell you that why it's blue. Okay, because all the white light is coming already, and it's a red cube, so it's always going to be red. But this portion is going to have some sort of reflection of this red ball, because from here some light is coming, and from all the possible angles. From here the light is coming, from here the light is coming on this object as well. Here is going to be some reflection. From here the light is coming to this point, or you can say from this point to this point, there is going to be a little ball being drawn here. And this, you can see this on mirrors, on reflecting objects, and this ball will be red ball. Okay, so what you'll see on the blue object, you'll see a red ball being drawn here somewhere. Okay, and now what will be the color of this cube? It's going to be mostly blue, but also some sort of blue plus red. It's not going to be complete red, because it's just not that reflective. Based on the reflectivity, it's going to be more redder, but it's always going to be blue plus red. This ball is on this is going to be look like blue plus red. This is why I said the colors are additive. Okay, and from this reflection the light is not going to stop. The light is going to bounce back here somewhere. Okay, again 90-degree angle. So on here, on this object as well, this red ball is going to have, which color is going to be this one? This color is going to be, wait, what is this? This color is, okay, how do I write? I can choose a text, right? Okay, I can't choose a text. Okay, I can tell you, but okay. This color is going to be what is this? Okay, this color is going to be the red plus the blue plus the green, because this object is green. So whatever the color, whatever the pixel color here will be, or whatever the real object color, if the objects are too shiny, here will be, this will look like the red ball plus blue plus green. So this will be the final color. This object which will reflect here will have the color only red and green. This will have red, blue and green, because it's getting double bounce. And this is going to be mostly green, but also some influence of red, mostly blue, but some influence of red. So that's how this is called ambient lighting, and ambients get lit because of these lights. And based on what are all the lights, the final color which are basically, this one, the final object color coming from here, here and here are going to be represented through what color on the surfaces are. So I think now you got the idea how lighting works in physics. I mean, how lighting works in real world. Okay, but the problem with this concept, there's a huge problem with this concept, and the problem is that we cannot render a billion light source. We don't have a billion lighting options, because I mean, there has to be a billion ray drawn from here, and whatever the ray bounces to here, only then calculate the red color is being reflected, and then that will go to here, and then that will go to here. And so we have to find out some way that, okay, I need to render this, and there has to be some way, but I don't want to, I don't have the memory, or I don't have the processing power to calculate for, or to compute for a billion rays. Okay, so there has to be a shortcut. So what shortcut we chose? We chose a simple shortcut, and if I could delete all of these, okay, so we did a very opposite method. Okay. In real life, what happens? Light is going to thousands of passes. It taking a lot of passes and drawing on everywhere, and only where it can. I mean, only where it interacts with object, that color it will take, and finally come to light, come to eyes. So what we did, we followed in ray tracing, we followed the opposite method which is presented here. Now this light is not a sun, this light is a light source. Okay, so for example, if the light source is there and there is to be some pixel being drawn, this you can assume that this is, yeah, you can assume that this eye is some sort of screen. Okay, and this eye is basically 1 pixel. Okay, so for example, this and size would be this. So for example, if we imagine a screen which we have to draw a picture. Okay, and on this picture there are going to, for example, I'm imagining a one-dimensional screen. So there is going to be 1 pixel here, and I have to render for 1 pixel from here, 1 pixel from here, 1 pixel from here. So all the pixels needs to be computed. Okay, the idea of ray tracing is that, so if I render from here, render from here, render from here, render from here, I need to calculate for all the pixel. Okay, got it. So let's see how we calculate for 1 pixel. So what happens in this one, we only compute, we do a reverse method in this one. Okay, in real object, light bounce follows like this, but we in this method we follow a opposite path. Okay, we look at this object. Okay, and then we saw that how many angles this pixel is making, how many angles are possible. We iterate through all the object that this is intersecting on which angle, on this angle. For example, if I draw 90 degree, it's going to be intersected somewhere here. So it will not be affected by this because this object is in between and it's not directly hitting this, but the ray will bounce from here to here. Okay, the ray will bounce to some blank space. So what color will be this pixel? The and then we also draw a ray to this source. Okay, so what color will be this pixel? This pixel will be the light color intensity. Okay, so light color will fall here, and based on at what angle it's falling, we have something called normal. Each object has a normal of its own, and normal is basically telling us that in which direction this object this object surface is bending towards. Okay, so normal goes like this. So we do a dot product through the normal, and based on that we calculate a color intensity and apply for that pixel. So for example, if this pixel is computing for this space, it's going to be only green color. But if the next pixel is computing for example this is space. Okay, if we are computing for this space, now we'll make the 90 degree angle and it will bounce to this. Okay, so we know that it's going to be green plus a little bit of blue, but this is also going to bounce to this. Okay, so we also know that there's going to be a little bit of red as well. Okay, so now we calculating red plus how we calculate how much blue based on the intensities. So we do a sort of reverse calculation from the camera point and from the light, and then we shine the light on this pixel, that how much light intensity is going to be there. Okay, so that is the concept which we came up, that there are not going to be 1,000 of light, but instead we'll calculate from the eye area that how many pixels we are going to compute for, or what color is going to be that pixel, how many colors are contributing to that pixel's performance. So for example, let me how do I escape? Okay, I can turn this off. Awesome. So if I search some more ray trace image, so whenever we talk about ray trace image, we talk about these images. Okay, here the light source is somewhere, and based on the light source the reflections are calculated. So in light source calculating, in ray tracing the calculating reflections are very very easy compared to the other methods like rasterizing. Here you can see the fire is there, and fire is affecting every single pixel. So you can see the here the intensity of the fire is contributing to the pixel color and all that, and the generated image is very very realistic. So this is RTX off, which means this is being rendered through rasterization, and in rasterization we have no good way of rendering lighting and all. But in ray tracing the accurate lighting is possible. So you can see the difference here. You can also see, yeah, in this image you can also see, in this image you can see some other ball which is basically this ball or this ball, but on these balls you can see the image of other balls. You can totally see the reflection from this, from here, from blue ball, from green ball. So each image is reflecting multiple times and all that. So yeah, always. So you can see in this ball there are a lot of smaller balls which are being rendered. Okay, so you can see there are multiple reflection bounds which can be calculated through these sort of reflectivity. This is the power of ray tracing, which is not possible with any other form of rendering. Okay, so you can see this image, and this will give you idea that we are calculating 100 of bounces, because this image is there, but inside this image you can see, in this image there is a little ball, and on that ball there are a lot of little balls. Okay, in here as well you can see some objects are highly reflective, some are not, but on all of them there are a lot of hundreds of balls being reflected. Okay, so these is very powerful technique of ray tracing, and ray tracing is used wherever the real wherever the realistic lighting is being preferred. But what is the why we don't use ray tracing all the time? Let me tell you the answer. So for example, an image is, let me open calculator. Okay, so usually an HD image which is 1920 times 1080 is going to be this many pixel, which means approximately 2 million pixel. 2 million, yeah, only 2 lakh 20 lakhs, yeah, 2 million. So 2 million pixels are being computed in once for rendering one single frame. So from as I already told you, I have to render from each pixel. I have to do all this process. From each pixel I have to throw a ray. Let me also show ray. Yeah, so the idea is to throw a ray from each pixel, okay, from this pixel, and then compute that how many colors this or what color this pixel should show. Okay, so I have to compute for each pixel. In this case I have to compute for to render one HD image, I have to compute for 2 million pixels in one single frame. Okay, so for one single frame I have to do 2 million calculations, and not just 2 million calculations, 2 million light ray will be there, and ray will basically do these sort of bouncing. For example, bounce from one object, and based on the light the object will take its color. Okay, so I can now explain a little bit of code that I built this ray tracer, and the concept which I just explained you, I built that concept in C++, which is a very it's a high level language, but you can also say it's a very beginner's language. Okay, so as you can see here, the same idea which I told you, in real world light works like this, but this is in this one the light works like this. So for example, for this light, for this particular pixel, what should be the color. So this is how the color is computed. All right, so I'm going to build a ray tracer. So building a ray tracer takes a lot of time. As you can see, there is a lot of mathematics, plus there is a lot of code which is involved. So I coded the ray tracer already. So for example, let me just go on my desktop. There are, I cannot see, hold on, what is this? What is the time? 10:49. Already we are 50 minutes down in just explaining what is a ray tracer. So I'm going to show a little bit of code. Okay, so this is simple C++. As you may already know, suppose if I cancel all the color, G++, and how do I compile this? I am already in that particular folder, in the ray tracer folder. All right, so I can type my class name, G++/C means compile, and then the class name, hello world. And okay, what is wrong? Oh, sorry, hello world.cpp. All right, and when I did that, it just updated. You can see the time is current time, hold on, 10:50, and this is compiled on 10:50, which means this is the file which is the output. You can see .o file is the output. And now, but the .o file is not executable. It's a mediator file, which is basically a platform independent file which you can use on some other platform, and it will recompile as any other C. It's basically .o file. It's a C++ way to understand that what is the code. Okay, so
Can the code, sir, can the code window be made to some extent larger? Code window?
yeah, it should be possible. It should be possible. Let me just check. This is not the code window actually. This this is the command prompt. I'll make sure the code window is larger. This is a little smaller, I do understand. Let me just find if I could make the size a little bigger. No, this is not the way. Yeah, when I'll do the code, actually I'll make sure I'll make the code bigger. Okay, so
Sure, sir.
yeah, so it has created hello world.o. So let me just run that file, hello world.o/o, which means from this file I have to generate an output file, and the output file name is going to be hello world.exe. all right, and we did that, and that hello world.exe is being refreshed. You can see 10:52 is the timestamp, and now to run the output, we can run hello world, just the exe name .exe, and that's it, and we got the output hello world. So that's how you will basically run your file. Okay, so what was the source code of C++ file? So I can either choose to open it on I have an editor called Sublime. It's a very good editor, but you can also edit it on Notepad. So for example, you can see it's a simple code which is include studio.h. Let me make the font bigger. Okay, now you can probably see. Okay, so include stdio.h, standard input output, and we are printing f, and this we are returning 0. So does anyone ever know that why do we write int main, or why do we write, or why do we return 0? So whenever we are returning here from this, so we are actually returning to whatever the operating system which is using us. So for example, when the hello world exe is being called, the exe is going to look for a main function, and the output from this exe is going to be some sort of integer value. And also we can also introduce string args, which we can receive as the string arguments to be used in there. For example, if we do that, we can also write hello world.exe space some sort of input, that my name, okay, and that my name is going to be processed, and the output could be hello string.args, which means hello Avi Dwivedi, or whatever the name you use. Okay, so that's how we do it. And where is my folder? Here is my folder. Okay, so I have written the Raytracer already. I'm going to explain some part of that. So I have built the Raytracer in two formats for you guys. Okay, one I have built for a binary Raytracer, okay, and the other one is a full-fledged Raytracer. So the full Raytracer I built a few years back, but the binary Raytracer I built just today, okay, from very scratch, to brush up my own understanding of Raytracer. Okay, so let's talk about vector 3. Does anyone know what is a vector?
So Avi, can I ask a question, please?
Yeah, sure.
So the coding that you're doing is C++, right?
Yeah,
Can we do this in any other language?
any other language. Yeah, you can choose
Oh,
any other language. You can literally choose Java, you can choose Python is the best way, and you can
okay.
also choose, I mean, it does not really depend on matter, it's just the logic, and you can use the logic on any other language you chose. Okay, so
Thank you.
hold on. Yeah, that's just okay. Okay, for example, if I have to, yeah, I can use this. All right, so let's talk about this section, and this is a vector 2, a vector 3. So does anyone know what is a vector? Okay, can we get some input? Do anyone know what is a vector? So in physics or in maths, we have vectors and scalars. Okay, these are nothing but the way to store values. Okay, for example, the way to store properties. And vector,
Can we say that vector can have multiple values? Scalar has
yeah,
one.
we can, yeah,
One.
yeah, exactly,
Yeah.
exactly. Vector and scalar both are the way to scale to say properties, but scalar represent just the one dimensional scale, or it's, you can also say it's a one dimensional variable, but vector is anything more than one. Okay, so for example, vector is either two-dimensional value, which means x or y, and if it's representing to the spaces, it's x or y, or if it's representing something else. For example, vector are very useful and very fundamental to mathematics. For example, if you are using any sort of physics, you can define forces as vectors. You can define a lot of things. In fact, color values could be defined as vector. And best thing about vectors, you can do a lot of mathematical operations in Cartesian coordinates and a lot of those. So here I'm also doing this. Okay, so I'm right now, I defined an operator. So for example, this is how you define operator. For example, I can now subtract one vector from other. I can define plus as well. It's going to be the same if I define a plus. Okay, so a simple operator is added. Let me just for simplicity define plus as well, because that will give you an idea that what I did there. Okay, so I'm going to copy paste this code, but how I'm going to define the plus operator? So I have to define what operator I'm going to define. Okay, and what is this is the output of this operation. Okay, the output could be a single float, a single double, or in this case, when I add one vector to another vector, the output is a bigger vector. Okay, that's it, that's how they are computed. So for example, the output is again going to be the same, vector 3, that's there. Operator is the keyword to define operator. This is the operator which we want to override. This is the vector, this is a sort of input vector. What is we are adding? For example, if we want to add a plus b, so for example, if we want to add a vector, where is my a plus b? Okay, if we want to add these values, the a is going to be the first vector on the operator is going to be this particular operator override, and the b is going to be this input vector, which we are treating as v here, okay, because it's as a vector. Okay, so yeah, and what are we going to return? So we are going to return in this case x. Okay, so this a already has a dot x, a dot y, and a dot z. Okay, so we can also use this dot x, y, and z. So but we are using x only because we can reference that. Here we are doing minus, but in this case of plus, we're doing x plus v dot x, y plus v dot y, and z plus z dot y. Okay, v dot y. Hold on. Yes. Okay, let me just close this window. All right, so we got this updated. So that's how we create, and rest is pretty common stuff. This is just declaration, which means this is what you call it, constructor, which means whatever you can decide values for these x, y, and z. Okay, let me also show you some more vector operations, like, because this talk is about vector operations as well, and it's very cool to imagine vector operations. All right, okay, so if we sort of have two vectors, which is, yeah, this is a very good image. So the plus operator which we just built is actually indicating this. So if we have this vector, by vector what I mean is, vector has two properties, orientation and a scale. Okay, orientation and a direction. Sorry, what I'm saying, orientation and magnitude, direction and magnitude. Sorry, yeah, the same thing, orientation and direction and magnitude. Okay, so this vector is a and this vector is b. So if you, for example, do a plus b, the output vector is going to be this big. Okay, is going to be exactly big as a and b, and it could be explained mathematically as well, but we don't have a lot of time to do that. Similarly, it goes to a, b plus c. So suppose if we walk for a units, then we walk in some other direction for b units, and then we walk in some other direction for c units, and if we plus add all these vectors, the output or the final vector is going to be equal to the a unit to c unit end. Okay, so that's how useful the vectors are. So yeah, it's the subtract works the same way, and all the operations works the same way. Okay, so we defined first our vector, okay, because we are going to use it a lot, and on the vector we do a very great operation which is called a dot product. So let me just explain what is a dot product as well. Okay, hold on. There are two things, dot products and cross products. So I'm going to explain dot product first. So here I have added the dot product. Okay, so what is a dot product? Let me just open that for you. Yeah, imagine you have two vectors. All right, where is this image? Yeah, imagine you have two vectors, vector a and vector b. In this one, yeah, this is the best image. Okay, imagine you have two vectors, vector a and vector b. Now what you have to imagine next, that a vector a is going to shine its light on vector b. For example, if we have a light source, where is that chunky thing? Yeah, how pin, epic pin. Okay, let me just make this a little smaller, and okay, hold on. Imagine if we have a light source somewhere here. Okay, this is a light source, and this light source is very perpendicular to, and or maybe we are caring about the perpendicular light to b. Okay, whatever the light is perpendicular to b. Okay, so we have to there is one more vector a, So we have to find the exact position, or basically the exact angle on which this or maybe at which angle this A will have its shadow on B. So the answer is somewhere here. Okay, but we have to basically define, we have to basically calculate this point. Okay, for example, if this vector is a greater vector somewhere here, okay, then where the shadow will fall, then the shadow will fall somewhere here. Okay, so if we have to, this is also called projections. If we have to basically define that how two vectors are compared, or what is the angle or of two vector in between, what is this angle and all those stuff. Okay, so then this then this equation is being used. Okay, so that when you calculate the dot product of these two angles, so that is basically you have to calculate the cos sine of this particular angle. Okay, and whatever the cos sine is, that the cos sine will give you the value between the -1 and 1, okay, or 0. Okay, when it will give you the value 0, when this angle is exactly perpendicular, it will give you a value of 0. When it's exactly horizontal or exactly equal, when the shadow is exactly equal, or you can also say the shadow is completely full, the value will be 1. Okay, when the shadow is in the other side, the value is -1, and here also the value is 0. Okay, so that's how cos work, and that is the whole idea of projections and the dot product. Okay, so yeah, I think we got it. And now let's talk about another term. Yeah, what do I do with this? Okay. Okay, so we are calculating dot, and these are the tools which we are saving for us to be used. Okay, now we have created an array. Okay, because we have to do a lot of ray firing from objects. So now we have computed array. Now I'm going to tell you how to decide array, how to basically calculate or create array. So that is the code for the array. I'm going to explain that in a moment. Yeah. So this is the definition of array. So as you can see, there is just an origin and a direction, and array is a limitless, or array is a limitless object which is going to infinity. So you have to define from which origin it is starting and from which direction it is going. So if I have to, okay, let me just turn this off. How do I drag it? Yeah, if I erase everything else, I supposed to erase, right? What is this?
Eraser is just above the black dot, Avi, sir.
Which one is this one?
Yeah, this one.
Okay, this one is erasing.
And I love the way you're using Canva for the explanation. Amazing.
Yeah. So Canva is a pretty nice tool. I just love it. In fact, I have a lot of designers, but I recommend them to assemble things on Canva because I love using Canva. Hold on, just erase that and turn off this one. Yeah. So if I use this tool, let me first make it smaller and use this line, the pencil. Okay, so if there has to be an origin and there has to be a direction. Okay? And origin is a vector. All right, so origin is a vector, direction is a vector. How do you define direction? So suppose if I define 0 0 comma 0 comma 1. Okay, so it's a vector pointing to a z direction. Okay, it's a one unit vector which is pointing to a z direction, and so on. Okay, so origin is wherever, at which point it's starting, and the direction is where it's basically pointing. Okay, yeah, so we got it. Now, yeah, so when you got the origin and direction, this is nothing but just a constructor, and we define this is basically the definition of a ray. Okay, it's nothing more than just the definition of our ray. Okay, so what is the next thing we need in this script? Obviously, we need to render something. So let's define the simplest object possible, which is a sphere. Okay, let me come back. Yeah, this is our sphere, and this has a simple function. Let me just reduce the font a little bit so that it's fit in Canva. Okay, sphere still not fitting. Let me just reduce a little bit more. Okay, so let me just pick this. So this is like you define ray, similarly you can define a sphere. Okay, so we have here defined a sphere. What we need for a sphere? Just a center, which is a vector 3 position. Center is a position which means it's going to be vector 3, and the radius. The radius is a double, just how many unit large is the radius. So for example, if I again show you my drawing skills, so here is some position, and if I define some sort of radius, some amount, so we can draw a circle or a sphere on top of this. Okay, so yeah, we got it. Awesome. So now what is the next thing we want? I implemented one more function in this sphere, specifically in this sphere structure. So let's take a look at that function, and that function is this function, intersect. Okay, so let's see how this intersect works. So this basically is checking the intersection between the sphere and any other ray. Okay, for example, if you have a ray as an input, you have to check, you have to return if it's intersecting with me or not. So if you know about circle intersection or sphere intersection, which is almost the same formula, it's a quadratic formula, which is basically b square minus 4c. Okay, so if you also look in here, you'll find this is the explanation. This is the this is also, you can say, the coordinate explanation. You can also calculate or derive the formula through this, or you can simply see here is also the intersection of circle, but ultimately the formula which we are using is this one. All right, b square minus 4ac, which is the quadratic formula which we are going to implement in this. Okay, so let me come back to this. You can hear what we are doing and how we are getting our A's and C's and B. It's defined basically here. So first we have to get ray origin and direction. So we need to know what we are dealing with. Okay, so and we also have the distance, but this distance is output. For example, if we got the hit, then we return through what distance the object is, or where did we actually got the hit, so that we can render the object in 3 dimensions. Okay, so yeah, so this intersect method is bool type, which means either if we are getting the intersection, we'll return that yes, we got it, otherwise not. Okay, so let's talk about this method, ray and direction we have. Okay, so first we have to calculate OC. So whatever the origin is there, for example, let me also start drawing. I'm very bad with that, but yeah, let's do it. For example, if we have draw red, where is the color? Yeah, okay, this is the origin. Sorry, this is the origin of ray, and this is the direction of ray. Okay, and we have to check that there is a let me change the color to blue. There's a circle in between, or there's a sphere in between. So sphere, what is the definition of sphere? The center and the radius. Okay, center and radius, and this is origin and direction. Okay, are they intersecting or not? This is what we are checking. So first what we calculate is O minus C. Okay, the origin of wherever the ray is coming minus the center. Okay, so first we are calculating this distance. Okay, when we do this, we define the operator. This is why we are able to do this. What we'll get is this vector. We'll get a vector from origin to direction. Okay, then what we are doing, we are calculating our B, because we need the B and C's. Okay, so B is going to be 2 times the dot product of OC and D. Okay, so OC, which angle is OC? OC is this. Okay, this is OC, and what is the D? D is this direction. Okay, so we are calculating the angle between this, right? You got it? So we are here, or you can say we are calculating the angle between this and this. All right, so got the idea, right? This B is going to be 2 times the OC. All right, 2 times dot product of OC and this D. You can also call it OD, but this is the angle which we are computing here, times 2. Okay,
Clear.
okay. Now C, talk about C. The C is going to be the dot product of OC and OD. Sorry, OC times. So dot product of OC and OC is again going to be 1. It's not going to be anything else. So it's going to be 1 minus R square, which is whatever is R. So R is the radius, R square, something like that. Okay, the C, we have the C. So here finally we are getting a disk. Okay, so this disk variable is going to check the intersection, that are we inside or not. Okay, so it's the formula finally, as we already know from this explanation, the formula is b square minus 4ac, and yeah, so b square we have, and a in this case is going to be 1 minus r square, which is going to be something in negative, and yeah, and c. Okay, so yeah, finally we calculated this formula. Now if this formula is greater than 0, okay, it's either be sorry, it's less than 0, which means we are definitely not hitting. Okay, because you may know that if we calculate this formula, either the equation is going to be minus, or since it's a quadratic one, or the plus one. So we are neglecting all the minus answers. So the answer is going to be somewhere in the plus one. If the answer is not negative, if the answer is 0 or plus than 0, then we have definitely hit somewhere. Now we have to, if I go to mouse and drag it down. Now if we have hit somewhere, now whatever the disk we have calculated, if you remember. So yeah, this variable. So minus b, b is the dot product which we calculated there, 1 minus r square. Okay, so now we are calculating both possible values of intersection, both possible distances of intersection. So since it's a quadratic formula, so on the positive side and negative side we are getting 2 images. Okay, so minus b plus disk, minus disk, and minus b plus disk. So we got t0 and t1. So whichever is smaller, we are going to take that one. So in the distance, whichever is smaller, that is our distance what we are looking for, and that is how we calculate intersection between these points. Okay, so now since we have calculated the intersection, we are ready to compute a binary image. Okay, so let's see. Where is our hello world? All right, this is our Raytracer. Okay, sorry. Okay, yeah, so after we have here color. All right, so color, you already know RBG, I defined in last class as well. We are here creating constant with 640 and 480, which means we are creating these size of images. Okay, so we have 640, and 480 we are creating, and we are right now using ppm for our output. We are creating an output stream ppm image because ppm is the simplest image which we can create from C++. If we try to create png, we need to include a lot of external classes, which I don't want to be the course of this, yeah, because that uses a lot of compression. So I'm using the simplest possible image file. This is ppm. Okay, so I'm going to output as render.ppm. This is the definition or the header of that ppm. So it's going to be p3. Okay, which means it's going to be 3 vector file, not 4 vector. 4 vector file will have the alpha value as well, but this is going to be 3 vector file, which means 3 channel file, which means it's going to have R, G and B values. We have the width which we have added, we have the height which we have added, which means the X and the Y's, okay, which is similar width and height. And then we specified that we are using 255 color channel. Okay, which means 255 is the highest value, which means 0 to 255 are the values. We defined the value of color 255 white. What is white? So white is for us 255, 255, 255. Black is for us this. We can also define, for example, red if we have to. So if we define red color, red, and red is going to be RGB. So and G and B are going to be 0. So that's how you define red or any other color. You can find the color code for your color. Okay, we defined a sphere. Where we defined our sphere, we have defined our sphere at half of the width. Okay, this is in pixels. Okay, so or about what is half of the width is 320, and this is going to be 240, and this is going to be 100, which means 100 pixels ahead. Okay, this is XYZ coordinates. And the second value, if you look at the definition of pixels, this is the radius, the sphere. So this is hold on, yeah, in the definition this is the vector, which means center, and this is the radius. So I need a 20 pixel bigger sphere at 100 pixel far from the rendering point, which is from the camera. Okay, for now our camera, we are imagining the camera as you can say the finally rendered output. Okay, so yeah, now what we have is, yeah, color pixel. We defined the color pixels. Okay, we created the one single pixel, and we are going to output that pixel in this. Okay, so we started a loop for Y. Again, this is going to be a nested loop for X. Okay, so we are incrementing that, and that pixel, we are going to have that pixel color, and that black. For now we are setting the pixel black by default. So for example, if we didn't get the hit, then we get the intersection, then there is going to be no color. We defined a ray. Okay, from origin and direction. So how we define the ray? We are defining the ray from the pixel. You can see it's X and Y. So for example, whatever the pixel at we are, okay, if we are at X at Y position, so we are defining the pixel like that, and we are defining the pixel here. We are defining the ray. For example, in the direction, the ray is going to be the origin and the direction. So this is the origin. Okay, at 0, yeah, means, which means we are defining this at the screen space. Okay, which means 0. And then vector 3, the direction is 1, means forward in the Z. So X, Y and Z, this is the forward. X is going to be horizontal, Y is going to be vertical, and this is the forward. Okay, now we have this double T, means 1000, which means this double is going to be how far the ray is going. What is the distance of the ray? And distance, it could be infinite, but we are choosing the distance as T. Okay, so here is the intersection which we are using it, and this T, if the T is 1000, we are starting at 1000, the ray maximum is going till 1000. But if the output of the intersection, as you already know, we ever taking the distance at the object is intersected or the object is hit with the sphere. So here we are doing, this is called sphere test. So we are doing the hit test. So we are firing the ray. We are telling that against which ray we are testing the hit. We are also going to test that if this the intersection is happening, put the value or change the value of this t. Okay. So if we are hitting something, the value of this is going to be changed. Okay. I'm going to comment this line because this line will slow down the process. And yeah, and then the final color. If we found something, suppose we render white, we can also choose any other color, like we just defined red, so I'm going to say red. Okay, so we defined red, we chose red. Okay, so now let's see the output of this code, and finally all the pixels are being output, and then program ends. So I hope you understood. I'm open for questions after this being rendered successfully. Okay, so this is the simplest possible way of generating an image through algorithm, which means this is the simplest rendering program ever. Okay, I'm going to render this. The file name is Raytracer and it's in the same folder. So G++ Raytracer.cpp, and it's compiled, which means it has created a new file here somewhere. If we look at the timestamp, we'll get the time. Raytracer.o, there must be a Raytracer.o. Oh, interesting. There's no output Raytracer. There, I have one more installation of the same, on which you'll also you can also use this method. Hold on. Yeah, I have this dev C++. There it is. Let me, for some reason this file is not compiled, so let me open the same file in dev C++. It's compiled, but the output is, for example, a hidden file, I think, because I cannot see the .o file here. Let me just open dev C++. I'm going to compile that on that. Okay, so this is dev C++. As you may already know, I'm going to open the same file, Raytracer. Yeah, this is our Raytracer file, the same code. I'm going to hit compile. Yeah, it's compiled successfully. We have 0 errors and 0 warning, which means it's successfully compiled. Do we have the O file? We still don't have the O file. I'm going to hit execute. So I'm going to run this. Okay, whenever I run this, now after running this, the output shall be here. Hold on. Okay, yeah, output file is this file. You can see this is updated, and you can see the output is a red image. Okay, can we move this image somewhere else? Okay, for example, if I try to move this image, how I'm going to do that? Let me just open the made the text a little bigger for you guys. How do I make the text bigger on this? Tools.
Mr. Sorry to intervene.
Sure, sure.
We have a vice chancellor. We have a vice chancellor, honorable vice chancellor, Professor Bhavesh Bhattacharya, and he is very worried because you know the font size as well as the visibility.
Yeah. I'm just working on that. I'm just trying to find make the font size bigger.
Yes, we have changed our resolution in order to match to yours, but if you can just increase the font size. So
I'm trying that. Just 1 second. How do I? Yeah, formatting options. Yeah, current font size. Where is tab width? Where is font size? Hold on.
Sir, please don't get disturbed. If others are able to understand, then it's fine.
Hold on, I'm just making the font bigger. Let me just search how do I make font bigger on dev C++. Dev C.
So actually, Avi sir, when he was explaining the code, he had the bigger font
Bigger
available in
font.
Canva.
Yeah, yeah.
Yeah, right now we're just seeing the execution, so it's okay. It's easy for us
Yeah,
to.
if it
Editor
is
options.
At least
others
I
are able
feel
to
so.
understand,
The
it's
others
fine.
can put in their. Yeah.
Editor
Right, sir.
options. Windows
Sir,
editor.
please don't get disturbed. If it is okay for others, it is fine. Absolutely.
No, no, just let me just find an option. I'm really sorry. Uh, does anyone know ever use this dev C++? Where is a font option? Because Control Plus is not working here. Formatting options is there. How do I increase font?
Sir,
Devs.
please don't get disturbed.
Okay,
Your
got
flow
it.
should not be disturbed,
Tools,
sir.
editor options, fonts. Okay, got it. All right, it's too big, I think. But tools.
So this is perfect.
Okay, now you can see the code, right?
Yes,
All
very
right.
clear.
So
Yeah,
how
yeah.
now?
Clarity is there.
Now the question is, how do we change our render? Okay, so now this is our output. How do I change this output? How do I render from any other point to see where is my image? So what we have to do, this is the sphere position. This is where we have created the position. For example, if I divide by 4, where you think it will be? It will be a little, for example, it's now in here, it will be a little here. So let's just recompile again and see the output. So if I go compile, if I go run, okay, we run this, and I'm going to delete, hold on, I'm going to open this image again. So as you can see, the image is shifted. All right, which means that is how we do rendering, the simplest form of rendering. But what is the
Sir,
problem with, yeah, sure,
sir, can the code file, C++ file, be shared with us so
yeah,
that
sure,
we can also?
sure, I'll share this with you, and I'll share one more with you. For example, if I increase the radius of the sphere, I want to increase the radius of the sphere like 50. Okay, I want to make the sphere a little bigger, and now I'm going to I have to do all this step again. So I have to rebuild, for example, compile and run. All right, it's updated. Now I'm going to run. Now you can see the sphere is bigger. So that is the science of generating images from the code itself, nothing but thin air of code. Okay, but I'm going to show you one more example of the same thing. Okay, which is taking in account of lighting as well. Okay, so I'm going to yeah, here I have worked on lighting as well. So I didn't get time to explain what is lighting and all that in one code, but I'll give you this code as well, in which I'm taking account of light. Okay, for example, here I have explained what is lighting. So what is the problem with current code? So the problem with current code is the sphere is red. It's super red. It is not any other color, and it's not looking like a real world object. It's looking red in each direction. Okay. Now how do I fix that? How do I make a sphere like a real object? It's I mean, it's like an object being rendered in real world. Okay. The answer lies in lighting. It does not have to be equally lit from all the direction. So let's see how I defined a light. Okay. So in this, here I have created another sphere called light. Okay, where I have created this sphere, I have created sphere at 0 0, which means it's in pixel space, which means it's in at the center. Okay, and sorry, it's not in the center, it's in at the left corner, left top. Okay, and this is Z50, which means it's somewhere in the world center somewhere in the world, 50 units ahead, and it's 0 0, and the size of this sphere is 1. So the light is nothing but just a sphere. Okay, or anything could be a light, a single point could be a light. Okay, that's how I defined a light. Now let's see where I'm using this light, or how I'm using this light. So after when we calculated the hit, after we got the hit, okay, that we got the binary sphere completed, which means now we have hit something. Okay, now we are going to account for that t. Remember that t which were in that the direction value in the output, that how far we are hitting the object. Okay, so now we are taking in account of that t. Now let's see what we are doing here. So we are calculating, first we are calculating the pi for us. Okay, that's going to be the ray of origin times dt. Okay, times ray dot d, ray of direction, times t. Okay, which means how far we are hitting. If I try to visualize that, let me show you. Okay, so this is our origin. Okay, this is our origin. I need first what we are getting. This is our object which we are trying to run. This is the light source somewhere. Okay, first vector what we are getting, the origin, and you know what is the origin, the ray is starting from here, so the origin is this. Okay, times origin plus ray times d dot t. Okay, ray of distance, what is the direction of ray, or times t, which means it exactly pointing to this surface, exactly here it's pointing. Okay, so nowhere else, just here. Okay, it's giving me this exact point on this surface. Okay, this is our render plane. Hold on, this is our render plane, and we are computing for this pixel. This is the line which is being drawn, and so this vector we are getting in this particular line, O plus dt. This is O plus dt. Okay, this is what we got, this particular point. At this particular point it's ending. Okay, now we are not making use of light, but imagine how the light is going to be used. Now we are taking in account of light. So light is going to be, first we are calculating this L is light dot c, which means light dot center, which is somewhere here, से लेकर एक line light minus pi. Okay, what is pi? Pi is this. Okay, from this vector. Okay, if we suppose from this vector we are calculating this vector, we are subtracting this vector, we are calculating this, we are drawing this line somewhere. Okay, c minus pi, this vector is this, so we are drawing this line. Okay, now what we are going to do, we are creating getting a normal for this pi. Okay, n is going to be the normal for this pi. Sphere dot get normal of pi. Let me show what is the, hold on, yeah, it's in sphere. Yeah, there is a normal function. You can see there is we have defined a normal function. This normal function is nothing but basically whatever the pi value is going to be there, it's pi minus center. So this is the pi minus center. Okay, pi, where is our center? Hold on. Yeah, this is our center. Okay, so pi minus center, what is pi minus center? This vector is my center minus this pi. Okay, this is going to be this vector. Okay, pi minus center. All right, so if we plus this is going to be this vector, if we minus this it's going to be this vector. This pi minus center is actually this vector. All right, got the idea? Pointing from here to here, it's pointing actually this way. Okay, minus r square, minus what is r square? This distance, r, so times 2. Okay, so this upon r square. So if we divide that center upon r square, so you can imagine this is the same distance divided by r square. So that's how that will give us a simple vector on this point. Okay, and it's pointing towards it's pointing like this. through this orientation, it will be pointing like somewhere like this. Got it? Finally, we got our normal on this, which is sitting on this sphere. So that's how we got it. And yeah, so since we got finally our normal, get normal in this, okay, now we can calculate this new dt. Okay, this new dt is going to be dot product of L dot normalize. We know what is L. L is basically light minus pi, which is this distance L, and the dot product of this normal. So here what we are getting, the dot product between the angle between, hold on, dot product is, you can also call the angle between this, so something like this. Okay, this and this. Okay. So finally we got our dt, and based on this dt we are going to add the intensities. Remember I told you the object intensities got added. Okay, so for example, light has a color. This light has a color. This light, which color this light has? This light has a white color. We are imagining this color, light has a white color. Okay. So that the new pixel color is going to be red plus white times dt. Okay, the light color times dt. Okay, so the light color, how much light is influenced based on this angle and this angle. So you got it already, that we are getting this reflection angle finally. Okay, so we got this reflection angle, and the w white dot times dt is this reflection angle. So red, whatever the red color is going to be there, plus the white color, which is the lighting color on this particular pixel, times 0.5. Why times 0.5? Because we are adding two colors, so which means intensity will be double. The red intensity is going to be there plus white intensity. So we are sort of averaging here by multiplying by 0.5, and then we are finally, for our safety, clamping this value, which means the value is going to be either in between 0 and 255. It's not going to be overhead of 0 or 255. It's going to be somewhere in between. Okay, finally we can finally render. So let me render this final outcome. Okay, so if I, hold on, yeah, if I try to render G++, hold on, where is the folder? Yeah, this is the folder, and the file name is raytracing. Yeah, let me delete these two files, because these are the outcome file which will be regenerated when we'll do this. Okay, so I'm going to G++ ray underscore tracing dot cpp. Okay, I've compiled, and the new compile file is has to be generated somewhere. So let me refresh, and there's no file being generated. Awesome. G++ compiler is giving some nakre here. So let me compile on that other compiler, which is dev C++. Which one is there? Dev C++ बंद कर दिया क्या मैंने? Dev C++. All right. So I'm going to open the same file on dev C++. Open this ray tracing cpp. Okay. Yeah, the same cpp file is there. I'm going to compile this. Let me hopefully think that it's going to compile without error. So it's looks like it's compiled. Let me just open, drag it a little. I'm sorry, I'm taking a little overhead of time, but it's compiled, zero warning, zero error, and I'm going to run this file. Okay, so I'm going to run. All right, so yeah, it's executed, and the execution is finished, which means it has created this output file. Okay, so now you can see the light is at 0050. The white light is there. As you can see, the white light is lighting up this sphere. Okay, now I'm going to show a little bit of magic. I'm going to turn the light color different. I'm going to make the light color yellow. Let's see what will happen. Okay, so what I'm going to do, I'm going to hold on. Am I connected to meeting? Because somebody is calling me again, and that person should not call again and again. Okay, yeah, everything is fine. I'm going to change the light color quickly for you guys, because one single image is not going to give you the perspective. So I'm going to change the white light color. So Yeah, ray tracing. Hold on. Yeah, this is the white color, light color which we are assuming. Okay, so I'm going to make the light yellow. How do I make light yellow? For example, let me fetch the value for yellow color quickly. Yellow color value. Okay, so yellow color value is 255 plus 255. If we make this value R and G, 255, it's going to be a yellow color. So let me just do that. Okay, so instead of white, let me define yellow color. Where we have defined white, hold on, inside int main we have defined. Okay, let me here define a yellow color. So color, hold on, where is white? All right. Okay, same way I'm going to define yellow. Okay, const vector 3 yellow, and yellow is going to be 255 plus G 255 plus 0. Okay, so this is going to be yellow light. So I'm going to change yellow light. Okay, and I'm also I can also change the position of the light, but I'm not going to do that. Let me just change this yellow. Okay, and let me execute this again, compile and run. I don't want it to use this compiler, but for some reason G++ compiler is not coming on, working there. Okay, so I'm going to double click that. You can see the light is yellowish. Got the idea? That's how you basically render. Let me move light a little bit and you'll see the outcome. Okay, so the light has defined somewhere its position. This guy has defined light here, so I'm going to move this light position from it's now in the x-axis. So for example, if I move the light w upon w times 2.5, w upon 2, so it's going to be in the center width. Let's see the outcome. So this is the previous image. Let me just recompile, compile and run. Now I'm going to move the light. Let me show the output for you. Now you can see the output is changed because we have moved the light from one position, and this is the previous. You can see the light is imaginary, but it's moved from here to here. You can see this is the later image, and so that's how basically this is the introduction to ray tracing. That is how
Wonderful.
ray tracing works.
Thank you for making it so easy, Avi sir. Thank you.
I hope you understand, but it's a complex subject, and it's actually the beginning of computer science. I'm disconnected from the web view. I'm really sorry. Yeah, I got disconnected. I'm really sorry I got disconnected. Yeah, so I hope you got the understanding that, yeah, and the second session is going to start. So best of luck for that. And this is literally the beginning of computer science and computer graphics. And we built our first ray tracer here. So I hope you got the idea. Okay, I took a little more time, but I think it's worth understanding the topic.
Thank you, Avi sir, for the in-depth knowledge and the clear and simple instructions for that. Thank you so much. And thank you, Soumya ma'am.
Thank you, ma'am. Any more questions from the audience, from the participants? Any more questions?
Yeah, if anyone has any queries, because it's literally just the beginning and there's a whole castle which we built on this.
All right.
I just had one query, Avi sir, quickly. I'm sorry
Yeah, sure.
You said there are two types of Raytracer code, right?
Yeah,
Which we have seen today.
two
You
types
named
of rendering. One is ray tracing and the other one is rasterization. So I only
that
covered
I
ray
noted.
tracing in this session. Yeah.
Yeah, that I noted. But in Raytracer also, you said we'll be looking at two types of things, and we saw two different types of codes.
Okay. The first one was the binary. Okay, it's in that one we were only checking the intersection. We saw two classes. The first one was binary. We were only checking the intersection, that is the object there or not, right? And if the object is there, what color should be that object, or which in more clarity, in the first one I should have rendered white base, which will make it more apparent that it's only binary. And for the second one I should have made it with the lighting and all. In the second one we were actually calculating the effect on each pixel of the light. Okay.
Thank you. Thank you for the answer.
Yep.
So we have one more query from one on the call. I think they want you to share the code file.
Yeah, I will share the code. I'll share the code. Connect with me on my mail or something, or maybe connect with me on my Discord channel or WhatsApp or whatever. I'll share the code. I'll upload the code on my. Okay, best way is going to be I'm uploading the code link on the YouTube session, in which this is right now already, as you can see, this is already the same session which is already on live. I'll put the code in the description. This is the best way to find it. Okay, I'll drop the code in the description. So come to XRDI TV, make sure you like it, or I'll drop the code in the description of this particular video. Okay, you'll find it here. Okay, so this is literally the simplest possible rendering in which we can do with ray tracing. And as you can already saw the example that how big engines work. So they do a lot of brilliant ray tracing and all stuff. So make sure you do that. And yeah, I'm getting a lot of noise, but yeah. So I think this is it for today's session. See you tomorrow, guys.